So, hello everyone. So, in this lecture, we'll discuss some applications of vector algebra to analytic geometry. Okay. So, one of them will be we'll try to understand straight lines in Rn. Okay. So, let us just write. So, applications of vector algebra to analytic geometry. Okay. So mainly we'll discuss about line. So at least for the next few lectures, and about line we'll discuss what is line, then mainly some properties, and we'll also try to understand lines as vector valued functions. Okay. or vector parametric equation of a line. Okay. So let us first, at least in this lecture, we'll try to understand the properties, some properties of lines. Okay. So let us just name this as lecture 1 for applications. So what is a line? So in R2, let's say this is the R2 plane. Okay, this is the R2 plane. So what we do, for to define a line, we need a point. We need a point through which it passes. Let this is the point P, and we need some direction. Okay, which is some vector. Okay, so both P and A are points in R2. Okay, so P belongs to R cross R. A also belongs to R cross R. Okay. The thing is that this P and A are given. So we want to find the equation of this straight line, or we want to find all the points of this line. Okay. So this will be generally denoted by L of P A. Okay. This is basically a straight line through the point P along the direction of A. Okay. Now if you come to the one dimension case, you have the real line. Again you fix some point P, take this direction A, the notation will be same. Okay. So in one dimension you will exactly get only the real line, right? Whatever line, you will get the real line. Okay. So this phenomena can be extended actually in Rn. Okay, in general. So how do you define it? So definition. Okay, definition of what? Line. Okay, so let n is bigger than or equal to 1. This is the Euclidean dimension. Okay, suppose P and A belongs to Vn. Okay, so Vn is the notation of Rn. Okay, this is basically mainly we are trying to understand vectors or application of vectors. So Rn is basically replaced by the notation Vn. Okay, so we say that, or what we should say, basically the thing is that we want to determine all the points of this line. Okay, the straight line, or like the line L of P comma A, which is basically passing through the point, passing through the point capital A along the direction vector capital A is defined as L of p comma A equals to p plus ta such that t belongs to R. Okay? Okay, so this is the line. So it passes through P along the direction of the vector A. Okay, so it passes through P. So that means the point, passing through the point P. It should be P. Okay, yeah, it should be P. So it passes through the point P. So this point is somewhere here, and suppose this is the line, and this is the direction A. So this is the point P. Okay, it passes through P along the direction of A, and all the points, you take any arbitrary point capital X, it will look like P plus Ta for some t in the set of real number. Okay, so as you vary your t, if you take depending on t, it will be basically infinite. Okay, it will go to the infinitely on the right side and on the left side also. Okay, yes. So so basically remark, what is the remark? The remark is, observe that this P should be in this line. Okay, so 1, let t equals to 0, then this point P plus Ta is nothing but P. Okay, so this should be in the line, right? Because all the points of the form P plus Ta is in the set. Okay, so this says that all the points of this set looks like P, capital P plus Ta. Okay, so in particular it has this form for every t belongs to R. So in particular, if we take t equals to 0, we get that P plus Ta is nothing but P. That means P is one point of the on the line. Okay, yes. Yes. So now if you take P equals to 0, okay, 0 0 0 in Vn, then L of Pa is exactly L of 0 comma A, 0 vector, which is Ta, right, such that t belongs to R. Okay, yes. So this L of 0A is basically all the lines passing through the origin. So if you consider in R2, if this is the origin, then if this is some vector capital A, then the line will be exactly this. Okay, so you just stretch it along both the sides in an infinite way, right? So this is Ta, or this is also Ta, right? Whatever, if this is negative, if this is positive, if t is positive, let's say. Okay, and this is your R2 plane. Okay, so similar phenomena can be understood as in higher dimension as a line through the origin along some direction capital A. Okay, also like when we define this, we take that along the direction vector capital A which is non-zero, okay, in the definition, because if capital A is 0, you will get exactly this point, okay, on this line, but we are mainly interested on line, okay, not only one point. Okay, so we do not get anything new if we take capital A equals to 0, right? Yes. So now we will try to understand some properties of straight lines. Okay, okay, so properties of, also we say that this is a line or straight line. Okay, line or just for to avoid confusion, we just write line or straight line both has the same thing. Okay, so properties of lines. Okay. Okay, so property 1. Okay, this is property 1. What does it say? So it says that you have two lines, let's say L of P comma A, that means the line passing through P along the direction of A, and you have another line which is the passing through the same point P along the direction of capital B. Okay, through the same point capital P, it says that they are equal if and only if A and B are parallel. Okay. So let us try to understand the statement first, then we'll try to go to the proof. Okay, intuitively. So what does it say? It says that you have one line, okay, passing through some point P along the direction of capital A. The other one says that you have another line, okay, let's say passing through the same point, okay, but the direction is different. Okay, yes. So if you just, maybe one can just change the colors just to understand. So this red one is L of P comma A, this red one, okay, and this blue one is L of P comma B. Okay. So what does it say? It says that these two lines will be equal, means all the points of this red line will be same as the points of the blue line L of P comma B, if and only if A and B are parallel. Okay. So I mean, at least from the picture it is clear, if A and B are parallel, okay, like this, A is this, B is this, okay, so you cannot get two different lines, right, because passing through the same point, right, if this is the point P, if it passes through the point P, now suppose they are parallel, they cannot be equal if it is the, I mean, they cannot be equal if they are not parallel, right? Yes. So intuitively it seems it is fine. And the other way, if they are equal, okay, if they are equal, maybe the direction of B may be different, either in this way or this way, or A also may be this way or this way, but they should be parallel. Okay, if they are equal, they must be parallel. Okay, so you have to rotate this line along the direction of A or along the direction of B. Okay, so let's try to prove it. Okay, so what will assume, let this way, if we want to prove, so let L of P comma A is L of P comma B. We claim that A and B are parallel. Okay, so we take any point on this line capital L of PA, okay, other than the point P. So this is the line, this is P, this is the direction. So we take any other point, let's say P plus A, okay, P plus A. So since P plus A belong to L of P comma A, but this point it belongs to this, but and this L of PA is nothing but L of P comma B, so P plus A also belong to L of P comma B, right? So there exists some S belong to R such that this point P plus A will be P plus some TB, sorry, this is SB, okay, That means that A equals to SB. Okay, yes, but but S is not equals to 0 since capital A is non-zero vector, right? Because when you have defined straight line, this A and B are non-zero vectors, it is assumed, right? Yes, so A and B are parallel. Okay, so A and B are parallel. Okay, now we assume that these direction vectors A and B are parallel. Okay, yes, so A equals to CB for some scalar C which is non-zero. Okay, so we claim that L of PA is L of P comma B. Okay, so that means what is this set? This is P plus TA such that T belongs to R, and this is the set P plus SB such that S belongs to R. Okay, so we want to prove that these two sets are same. So we'll prove that both of them are contained in the other. So first we assume that there is a point capital X which is in this set. We'll prove that X belongs to P plus X belongs to L of P comma B. That means X equal to P plus TA for some T belongs to R. That means X equal to P plus T CB since A equal to CB. Okay, but TC is in also an R. That means X belongs to L of this. Okay, so L of P comma A is a subset of L of P comma B. Okay, what about the other one, right? So let we have Y in L of P comma B. That means Y equal to P plus some KB for some K in R, which gives that Y equals to P plus K by C into A, since A equals to CB and C is non-zero, so we can define by C. That means that Y belongs to L of P comma A. So L of this is a subset of L of P comma A. Okay, so if this is equation 1, I mean relation 1, relation 2, so from 1 and 2 we get L of PA equals to L of PP. Okay, so this is the analytic proof of this fact. Okay, so what we proved is that we had two lines passing through the same point with some directions A and B, may be different or same, we don't know, but we have given some sufficient condition on the equality of such two lines, which says that they will be equal if and only if the direction vectors are parallel. Okay, now we will prove the second property, property 2, which says that L of PA equals to L of Q comma A. I am not writing what is this. So this is basically you have given some capital P and some capital Q, two given points, and this is the line L of PA is basically through P in the direction of A. This is the line through Q in the direction of A. Capital A is non-zero. They will be equal if and only if Q is in this on this line. Okay. Okay. So what is the proof? What is the idea first? So we have two different points. This is P. Let's say this is the line L of PA, and we have some other point Q with the same direction A. So this should be also B. Okay. So this is Q. Okay. Yes. So now it says that these two lines will be equal if if and only if Q is in this set. Okay. So it says that suppose they are equal. So So they will be equal. You can see that this line has to be on this line. So Q must be here, right? On this line. So Q should be somewhere here. Now suppose Q is here on this line. That means the line, if you have 2 points on the same line, by definition, or just by the definition, the line, basically this line is L of P comma, if this is Q here, okay, so along this direction, since Q is on this line, so the line through Q in the direction of A will also be this line, right? At least from the picture it is fine. So let's prove it, okay. So let L of PA equals to L of QA. So how do you want to prove? We want to prove that, so we want to prove that Q belongs to L of P comma A, that is, there exists some T in the set of real numbers such that Q equal to P plus TA, right? So we know that P plus A belongs to this set, okay. Since L of PA is L of Q of A, so that means that this, basically this says that this is nothing but L of PA, this set is nothing but L of QA. So we are just replacing L of PA by L of QA. So it says that P plus A belongs to L of QA, but that means that there exists some S in R such that P plus A is equals to Q plus SA, and that means that Q equals to P plus 1 minus S into A, and this is nothing but 1 minus S is again a real number, so this is in the set or on this line, right? There's some point. So that means Q is in L of P comma A. Now the other way, okay. So let Q is in L of P comma A. So what I claim is that the line joining through P along the direction of A is nothing but the line through Q along the direction of A. So again, let X belongs to L of P comma A. That means X equal to P plus TA for some real number T, but Q is in L of P comma A. So since this, so this implies that Q equals to P plus SA again for some S in R, okay. This dot 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 means for some, okay. So what I want to prove is that X belongs to L of QA. So what we get, we know that this is P plus TA, but from here we know that P equals to Q minus SA, right? Okay, we put the value of P from the second equation, so we'll get that this is nothing but Q plus T minus SA. So this is in the set L of Q comma A. So this we have started from L of PA and proved that X is in L of QA. So we have shown that L of PA is a subset of L of QA. So this is one equation. Now let Y is in L of QA. So that means Y is equal to Q plus SA for some S in R. So this means P plus maybe S1 we can write because we have already chosen S here. Now we put the value of Q because Q is given in LPA. So we get that this is equal to SA, put the value of Q plus S1A, nothing but P plus S1 of A. But S plus S1 is again a real number, so this belongs to this set. So what I get is that L of QA subset of L of PA equation 2. So from 1 and 2, we get this. Okay. So this second result also gives some sufficient condition on equality of two lines, but with along different points, okay, with the same direction. It says that they will be equal if and only if one point should be on the other line. I mean, you can replace this by saying that P belongs to L of Q comma A. This, the reader should check that this is in fact same to this fact. Okay. In a similar way, just try to play around with the point P. Okay. Similarly. Okay. Yes. So this somehow gives some nice criteria to check when two lines will be same. Okay. So now we will define two parallel lines. Okay. So definition of parallel lines. Okay. So two lines LPA and L of Q comma B are said to be parallel if A is parallel to P. Okay. Okay. Yes. So this is the definition of two parallel lines. So it exactly says is that you may have one point P here with the direction of A. You may have some different point Q. These two lines will be parallel if the direction vectors A and B are parallel. Okay. Like these two lines are parallel. This is L of P comma A. This is L of Q comma B. Okay. Now we will prove another property. 3. It says is that you have given a line capital L and a point Q not on the line, not on this line L. Then it says that like here, suppose this L of P comma A is given and this Q is not on this line L of P comma A. It says is that there is, you can get exactly one line along this point Q which is parallel to the given line L. Okay, that means L of P comma A. So then there is one and only one, or there is a unique line L dash which contains or containing Q and parallel to capital L. Okay. So how will we prove it? Okay. So what does it say is that you have given some line capital L and you have some point Q. So of course this line will go through some point P. It will have some direction. Okay. So let L has the direction capital A. Okay. Capital A. Okay. Now we define L dash. Okay. So basically there are two parts in this statement. One is that there is a, it says that there is the existence and also unique. So first we will try to prove the existence. So what can be this L dash? Okay, this is L dash. Maybe this is not the correct symbol. This is fine. Okay. So it says that L dash. So what is a line containing Q parallel to L? So if this is the direction capital A, then of course by definition of line, this is one of the line. Okay. That contain the point capital Q and with that along the direction of capital A. Okay. We want to prove that this is unique. Okay. we want to prove that this is unique. Okay, so what is L dash? L of q comma a. Okay, let's forget about p because we are not really bothered about p, right? Okay, we only want a line which passes through the point capital Q along the direction of the line, given line L, that means along the direction of the vector capital A, which is this line L prime. Okay, now we want to prove that this is unique. Why this is unique? Okay, so if you remember, we want that this must be parallel to the given line. Okay, this is also parallel. Okay, then capital L dash contains Q and parallel to the line capital L by the definition of parallel lines, right? It also contains Q by the definition of line, right? Yes. Why this is unique? Okay, suppose there is another line L double prime which contain Q and parallel to the given line capital L. Okay, but we proved that if we have two lines L of PA and L of P comma B basically through the same point, okay, through the same point, so basically what I am saying, so let L double dash be a line containing Q and parallel to L. Okay, another line. So by the first theorem or first property that we proved, which says that if you have two lines passing through, let's say, the point Q, okay, and you have, let's say, two direction A or B, A and B, it says is that if these two vectors, if A and B are parallel, the direction vectors are parallel, these two lines must be equal. Okay, so it says is that L of QA equals to L of QB. Okay, so this L dash contain Q parallel to L, capital A, let's say, that is the direction of capital L. L double dash also contain this point, so basically L dash, sorry, this L dash contains this point and this is the direction L dash. L double dash is also contain the point capital U passing through parallel to L. Maybe that L double dash may have some different direction, let's say this direction, but this is L double dash, let's say L of Q comma B, okay, or some TA instead of A, and this is L of Q comma A. So we can write that by property 1, L is L double dash. Okay, so this is the uniqueness. Sorry, L dash is L double dash. Okay, yes. So this proves the uniqueness. Okay, this is L dash. Okay, so here we stop this lecture. From the next, in the next lecture, we'll prove some more properties of straight lines. Okay.